This is the second video in the thermodynamics series. This one we're going to talk about calorimetry. And calorimetry is a way to measure heat flow, another way to measure heat flow, just like when we were talking about heat energy. The heat flows either into or out of the system, or that the system is just the substance that you're studying. But the calorimetry is just a formula that you use if you have the specific heat capacity of a substance. And I'll explain what that is. Specific heat and specific heat capacity are the same thing. They're just used interchangeably. So the formula for this, for the calorimetry formula, and really that's all it is, don't be scared of the word calorimetry. It's just basically the formula that you use to determine how much heat flew in or out of the system if you have the specific heat of the substance. Because as we said before, you can't actually measure the heat flow, the heat energy that's either goes out of or comes into the substance. What you can do is you can measure the other things around it and then determine by that what the implication of the heat flow was, what is implied for the heat transfer. So this is going to make a lot more sense in a second, but the formula is Q equals capital C times lowercase m times delta T. Now C is capital C specifically is the specific heat capacity. Just think capacity and capital C capacity. So that's the specific heat capacity, and usually in the formula you are given that. You don't have to figure it out for yourself what the specific heat capacity is for that substance. You're just given that for in the problem on your test. Now the specific heat capacity, what it is the amount of joules, or the amount of heat in the unit of measurement joules, that is needed to raise just 1 gram of the substance, raise the temperature up 1 degree. So 1 degree of 1 gram in joules, how much heat is required to raise that temperature. Now, here's the thing about the temperature. It can be in Celsius or it can be in kelvins. It does not matter. It's going to be the same number. So you really can do this formula with Celsius, or you can do this formula with kelvins. If you're given a mix in the problem, like you're given Celsius for one thing and you're given kelvins for the other, you can mix those up. That's totally fine for calorimetry. Now, so therefore, since the amount of joules of heat is required to raise 1 gram of the substance's temperature up 1 degree, specific heat capacity, or capital C, is going to be given the unit of measurement joules per grams times Celsius, or joules per grams times Kelvin. So as you can see in the bottom here, that's joules with a divisor bar and the grams times Celsius, or joules with the divisor bar and the grams times K for kelvins. So that's what that is the unit of measurement that you're going to give the specific heat capacity in. So the specific heat capacity, again, is this capital C. And it's the same capital C up here at the top of the page in this formula, the Q equals Cm delta T. So as we just said, the capital C is specific heat capacity in joules per grams times Celsius, or joules per grams times Kelvin. The M in the calorimetry formula just is mass in grams. And then that delta T, that triangle T, remember we said in the first video, you can put a triangle in front of anything, and it just means the change in the amount of that thing, of whatever you put the triangle in front of. And the triangle is called delta. Here, delta. So, and this temperature, this is going to be the change in temperature, since the triangle is in front of the big T for temperature. Now this can be in Celsius or kelvins. It doesn't matter because it's just a change in temperature. So like 32 degrees Celsius and the temperature is lowered to 30 degrees Celsius is going to be 2 degrees. 298 kelvins and lowered to 296 kelvins is going to be 2 degrees. It's the exact same thing. So it doesn't matter if it's in Celsius or kelvins. And then the Q in this the calorimetry formula is going to stand for the heat in joules that's required to raise the temperature 1 degree of 1 gram of that substance. So here's an example problem that goes with this formula, and see, you have the specific heat is given to you in the formula. The specific heat of octane is 2.22 joules per grams times Kelvin. So since you were given the specific heat in this formula or in this question, then you know automatically to use the calorimetry formula with the C in it, the capital C for specific heat. So the specific heat of octane, and that's C8H18, is 2.22 joules per grams Kelvin. How many joules of heat, that's the Q, how many joules of heat are needed to raise the temperature of octane from 10 degrees to 25 degrees? So all we have to do really is glean the numbers from this question and plug them into the formula Q equals Cm delta T. So here it is, the specific heat of octane is 2.22 joules per grams Kelvin. How many joules of heat are needed to raise the temperature of octane from 10 degrees to 25 degrees? So the Q is the heat in joules that the question is asking about. The capital C, the specific heat, is given to you. See, and I think probably most of your test questions on this, they're going to give you the specific heat. They're not going to make you figure that out. So if the question has specific heat in it, then you'll know to use this formula. So the specific heat is this capital C, 2.22 joules per grams Kelvin. The mass, the lowercase m, is, I already figured it out for you for octane, but you can just figure this out for yourself if you want. It's C8H18. And that comes out to 80 grams, 80.0 grams is the mass. And then the delta T, the triangle T, just means a change in temperature. The change in temperature is 15 degrees. Now, again, it doesn't matter if you put down Celsius or kelvins, if the question asks Celsius or kelvins, as long as it doesn't ask Fahrenheit. But but if it asks either Celsius or kelvins, it doesn't matter, because regardless, it's still going to be 15 degrees. 15 degrees Celsius or 15 degrees kelvins. It's just going to be 15 degrees because Celsius and kelvins have the same quantity in their degrees. Their degrees are equal to each other. So here's the Q equals Cm delta T. Q equals, and then the C is the 2.22, and always write down the units of measurement so you can know that you're canceling them out correctly when you do these kinds of formulas. Because if they don't cancel out correctly, then you didn't remember the formula right, or something's wrong. So 2.22 joules per grams Kelvin, and that's going to be times, so I'm just going to put parentheses around it so it's easier to read, times the mass, which is 80 degrees, 80.0 grams, times 15. And that 15, as we said earlier, could be Celsius or Kelvin, doesn't matter. It's 15 degrees. So when these go to cancel out, these units of measurement go to cancel out. This Kelvin over here, let me change colors. This Kelvin over here in this part of the formula, the specific heat part, this Kelvin is going to cancel out with whatever you have over here, whether it's degrees Celsius or kelvins, it doesn't matter. They will just cancel each other out. So cancel and cancel. And then this gram in the specific heat, the 2.22 joules over grams times Kelvin. The Kelvin's canceled out. That gram cancels out because of this gram right here, the 80 grams, 80.0 grams of the mass. Leaving, the only thing left is the joules for the unit of measurement. So you know the end result of this question is going to be joules. And that's exactly what we need because the formula asks the question, what is Q? And Q is in the unit of measurement of joules. So you can pause this and punch this into your calculator if you want. I had already figured it out for you. The answer is 2,664. And that's joules because the other units of measurement canceled out. But we need to go back and we need to find out how many significant figures there are so we know how to round this. Now there are, in the specific heat, there's 2.22 is the number, so that's 3 significant figures. For the mass, that's 80.0, so that's 3 significant figures. Temperature doesn't count. You never count temperature in significant figures. So we have both of these, we have 3 significant figures. So our final result is going to be rounded to 3 sig figs. So 1, 2, 3, and let's draw a line after the 266. That 4 rounds down, so it leaves the 6 as it is. And we have to put, since this is, since we have one more digit to get to before the decimal point, we have to put a filler 0 in. So the answer is about, this wavy equal sign, that's what it means, about 2,660 joules.